health monitoring, basically it involves continuous monitoring, because we have to get the information about the structure, critical responses of the structure, and the loading environment. They are dynamic, they are not static, they continuously change. So structural health monitoring we have to do long term, at least long term. So long term, when we say, is a relative. For some structure or some judgment of engineer, long term could be 10 years, and other case it could be 6 months. But essentially, the period should be long enough so that we can have one measurement and comparison we have another measurement. So on the basis of 2 time frames, we can derive some decision. That is structural health. Conditional assessment is, it's just one time. Just like we have the feeling that I am not feeling well. Let me get my liver function test done, kidney function test done. I just walk in, get the test only one time. That is conditional assessment. So conditional assessment, there are several techniques. For example, bridges, there are those load tests are there. IRC code very clearly prescribes what procedure should be adopted. So that is conditional. So structural health monitoring, basically it involves a long term, because we are dealing with the loading environment and the responses. So it has to be long term. Now another term is non-destructive evaluation, because often I am bringing these terminologies because many times these tend to be confusing and people try to use them interchangeably, but they have fine difference. Now non-destructive evaluation technique, these are basically the techniques used in the industry for assessing some parameter without causing any kind of damage or breakage. Otherwise, in civil industry, if we have to test the strength, we have to do field testing. So if we can do without that, without core cutting or without any of these measures, then that is non-destructive evaluation. So industry has a lot of techniques. We have limited non-destructive evaluation techniques in civil industry, but mechanical industry has huge number of ND techniques. We have magnetic particle tests, they have imaging technologies, they have radiography, they have acoustic emission. A lot of practical techniques the mechanical engineering industry uses. Compared to that, we have civil engineering fraternity, we have a small case. So this is non-destructive evaluation. But what is the relevance to structural health monitoring? Structural health monitoring means continuous evaluation. So structural health monitoring process may employ one or more of the non-destructive evaluation techniques. So that's how the two are related. Now another term is structure audit. So what do you understand by structure audit? Often the layman, they think that structure audit is something which will solve every problem. If they find that now the structure they are being run to failure maintenance, run to failure strategy. So now the problems they have started coming visibly, and they are seeing some cracks, and those cracks are quite big, and they are seeing some rebars exposed, and the rebars are found to be corroded, and similar kind of things. So now run to failure strategy, what they do, they say, okay, let's employ someone who can do structure audit. So audit is basically, it's a kind of evaluation of the structure done by experts. And what in mind? With the aim of finding whether the structure is compliant to code or not, and to get some subjective assessment of the condition of this. Usually aided by visual inspection or non-destructive evaluation. So essentially it based on the experience of the expert. The expert goes, he studies the design, he may ask, okay, please give me the drawings of the structure calculations, and he also gets done some non-destructive evaluation tests to know what is the residual strength of concrete. So aided by this, based on his expertise, he says, okay, this is the situation, and if this is the situation, whether the structure is compliant to codes or not. Often this is the main issue, that the after some kind of tremors, the owners they get alarmed, and then they often approach some agency to assess whether this is suitable, this is good enough to withstand earthquake or not. So that is that comes in the category of structural audit. Now structural health monitoring is much higher. So structural health monitoring is basically a data-driven process. And what data? Data from sensors. So first of all, it has to be long-term enough that we should make a judgment in relative sense. That okay, 6 months before this was the outcome, and now it is this outcome. So that we are able to compare one of the time frame we use as a baseline. So that is structural health monitoring. So it's totally based on sensor data driven. It's more objective. But there is a connection. If we have structural health monitoring system in place, then structural audit can also get better, because then we can take very informed and very scientific decisions based on the sensor data. Sensor data we are getting for 6 months or 2 years, and based on that we can take very informed decisions about the condition of the structure. So that is the two structural audit and structural health monitoring we are doing. Now, what is the current perception of structural health monitoring? Current perception of structural health monitoring, I am just comparing civil engineering fraternity with mechanical engineering fraternity. So if they make a small product, even the smallest product will have lots of sensors. Say our mobile phone, even the most inferior type smartphone, it will have accelerometer installed inside. It will have different sensors to sense the light intensity, and many more sensors. Whereas we are building our structures, we are leaving up to the design stage. We do all calculations, we run on the analysis software, code analysis software, STAD or PDABs, or more complicated structures, we will do finite element analysis using ANSYS. But what happens after the analysis and design stage? Everything is left to the contractor, and apart from the cube tests, nothing else is done. We are not bothered that okay, our estimation suggested that this would be the bending moment at this point of the structure. But what is the actual bending moment? We estimated this would be the design load on the column. So after the building is constructed, now it's started using. Now what's the actual load on the column? You don't measure. Our bridge is there, and bridge, when the vehicles are moving, there are static and dynamic deflections. Are we within limits? Because we just leave after the calculation. We just do calculation, the limit state of service will be checked, we calculate, okay, based on the dead loads and the post load, this would be the deflection. We are just limited to calculation. Have you ever bothered to measure the actual deflection in a structure? Seldom. Only when if there is a problem, then we may measure, otherwise not. So our perception, we have to change our perception. We have to be more tech savvy, just like other disciplines, and we should also base our decisions on measurements, not just on simple perception, visual perception, or the expert opinion. But we should change our system and make it more advanced so that we rely more on sensing data. So current status of structural health monitoring is that it's recognized as a crucial element, but then action on part of the authorities and the users that often lacks, and since it's not part of the portal requirements, so it's not mandatory, desirable but not mandatory. Then the thing is that when we suggest some user to implement some structural health monitoring technique, the first question is what's the cost? And often the users, the builders, or the owners, they are skeptic about the cost issues. That they are wondering if we really invest this much money in sensors and in the data acquisition system, what will be my benefit in the long term? That question is always there. Then the last one, technology obsolescence. Every month we find newer and newer technologies they are coming. New softwares, new interfaces, new sensors. So it's very fast changing world. We deploy some sensor and in just a couple of years, then that becomes obsolete. New operating systems come, new versions of the Android come, the software obsolescence is there, then hardware obsolescence is also there. So that goes on. So many times it happens that the sensor is not compliant with the new operating system. So this obsolescence also adds to the confusion. But is structural health monitoring a rocket science? So we are just going to see how we can have a beginning in the area of structural health monitoring. Very simple, with simple instrumentation, simple cost-effective devices, we can at least begin some form of structural health monitoring. It's not a rocket science. So that was the background, and I hope it was not a repetitive. Okay, that's good. And there may be a little bit repetition here, one or two slides, just for revision. So we define smart materials. So can you name any smart material? Yes? Any smart material? Sorry? Fiber optic sensors, yes. Any other smart material? So what is a smart material? So smart material, they exhibit stimulus response characters. We apply any stimulus in the form of a parameter, structure specific parameter like stress, strain, and we get some kind of signal in another form, and that signal is carried. So this is the class of smart materials. So here we have four commercial smart materials are listed. You have rightly pointed at the optical fiber. So today's modern communication is happening because of optical fibers, and the principle is total internal reflection. The light is passed from, say, here India, and in between there are amplifiers, and light signals they are able to reach the other part of the globe, and that's how internet is working. So this is the optical fibers and shape memory alloys. So they can remember a specific shape. So shape memory alloys, they are used in the medical industry. The angioplasty, any person has to do angioplasty, then shape memory alloy stents they are used. The electroneurological fluids, they can change their viscosity upon subjected to electric fluids. They are used in the defense sector. And piezoelectric materials are there in our everyday use. Everyday use we are using numerous applications of piezoelectrics. So we will focus here on piezoelectric materials. So here I have brought some simple demonstration also, that demonstration. So piezoelectric materials, they tend to develop internal dipoles. If you stretch So it has a tendency to develop internal dipole, and that leads to accumulation of charges. So when charges are there, that means an electric field is produced. So the behavior is just like parallel plate capacitors. Parallel plate capacitors, when you apply an electric field, charges are accumulated. So here the charges are accumulated even if you stretch a little. So the commercial, here I have listed some of the chemical compositions of commercial piezoelectric materials like quartz, silica, then lithium niobate, lead zirconate titanate, and lead lanthanum zirconate titanate. So basically, here the number 3, lead zirconate titanate, is today the most widely used piezoelectric. So basically, they have the direct and converse effect. So this slide would be a repetitive, but I'll give here one experimental demonstration of the direct effect. So converse effect equipment have not brought. So direct effect means that you apply a mechanical stress, and what we see is the accumulation of charges. So that is the signal. So here the stimulus is our stress. We apply stress, and the response is in terms of the charges. And when there are charges, then from the theory of parallel plate capacitors, there will be a voltage also, and electric field also. So electric field is basically potential difference per unit distance. When there is electric field, there will be an associated potential difference. So this is the direct effect. So direct effect, when we say piezoelectric direct effect, we are talking about the dynamic condition. So I'll demonstrate you the static and dynamic condition. So it works when there is a dynamic stress. It does not work efficiently when there is static stress. So under dynamic stress conditions, we can get a very good sensing done by piezoelectric materials. And similarly, there is converse effect when you apply an alternating electric field. What happens is, again, there is development of phase. So this is the converse effect. That opposite of the first phenomenon is happening. The first phenomenon, we are applying stress and we are getting electric field, but here we are applying electric field and we are getting some kind of phase. So if we are applying alternate electric field like this, what we will see this kind of vibration. So I am just now just starting my oscilloscope and show you the direct and the converse effect. And what I have done is that, so that everything is projected here, and just in my presentation I will sit on this camera. This camera sits on. So I will just place this so that oscilloscope is visible to everything. This experiment we have demonstrated? Yes? Oh, the direct. You are able to see the oscilloscope, and now here is a sensor. Okay, so this is a sensor. Let me just focus. Yeah, now the focus is okay. Visible to everyone? Yes.